How can a mouse lift an elephant? They just need leverage. When you took statics, you learned about moments and how a force with a longer leverage arm can generate a larger moment. Well, in fluid mechanics, hydraulics provide another method for obtaining mechanical advantage, and that is through pressure. In this fun video, we're going to do a super quick mini lecture about Pascal's Law and Pascal's Principle to learn how forces are distributed throughout a fluid as pressure. And then we'll find out exactly how a mouse can lift up an elephant the same way that a car mechanic lifts up a car using a hydraulic lift. Archimedes said, "Give me a lever long enough and I will move the world." The lever is a way to obtain mechanical advantage that a small force with a very large leverage arm can create the same moment about a stationary pivot point as a very large force with a very short leverage arm. And this ratio of the two distances is called a mechanical advantage. It's a ratio as to how much larger the output force is than the input force. In hydraulics, mechanical advantage can be explained through Pascal's Law, also called Pascal's Principle. Applying a force to a contained liquid creates a pressure as force divided by area. And that pressure is immediately transmitted to every surface in contact with that fluid. So for this drawing of a hydraulic lift, applying a force on one side creates pressure that pushes outwards on every surface, up, down, left, and right. The same pressure everywhere. And a mechanical advantage comes from the surface area. Since pressure is force divided by area, a very small area on one side will create a large pressure. So then on the other side, if you have a very large surface area, that same pressure will act over the entire large surface area and generate a very large force. And in some ways, this is the same but exactly opposite the way leverage was used back in statics. In statics, a longer leverage arm was more mechanical advantage. So this way, you see if we rearrange the terms, a small input area and a large output area is how you generate a large mechanical advantage. So let's put some numbers to this and let's see how our strong mouse can do. So suppose our mouse is 0.05 pounds and the baby elephant is 500 pounds on the other side. So the mouse's piston has a diameter of 0.2 feet, just a couple inches. We'll assume that they're actually at the same height for this first example. What we want to find is how big of a diameter does the elephant's piston need to be in order for the mouse to be able to balance him? Fluid mechanics problems always require assumptions. For this problem, we're going to be ignoring the mass of the pistons and we're going to assume that they're frictionless. This lets us ignore the pistons entirely and just think about the mouse, the elephant, and the fluid. We are going to need some material properties for the fluid, so let's assume a standard specific weight of water of 62.4 pounds per cubic foot. All right, let's knock out this first example problem so we can take a break and play with your TA Indy over on his treadmill. Since the mouse and the elephant are at the same elevation, they're going to be at the same pressure acting on both pistons. So if pressure 1 equals pressure 2, that means the weight of the elephant divided by its surface area will equal the weight of the mouse divided by its surface area. And plug in the 500 pounds, the 0.05 pounds, the diameter, 0.2 feet for the mouse. And we get a diameter on the elephant's side of 20 feet. So if the elephant is standing on a 20-foot diameter piston, this mouse will perfectly balance him out. That is huge. A 20-foot diameter piston is enormous. So unfortunately, this very first example problem, not super realistic yet, but it does help us generate a little bit of intuition. Notice that the diameter of the elephant's side versus the mouse's side is 100 times larger, from 0.2 feet to 20 feet. But the difference in their weights is 10,000 times, 500 pounds versus 0.05 pounds. And this is because area is based on diameter squared. Doubling the diameter doesn't double the mechanical advantage, it actually gives 4 times the mechanical advantage, 2 squared. So a 100 times larger piston gives 10,000 times mechanical advantage. But even still, 10,000 times mechanical advantage was not really enough to give a realistic size for this problem. So let's help the mouse out a little bit. For this next problem, we're going to say that the mouse actually has a little bit of a height advantage also. That the mouse's piston is standing on top of a 1 foot tall column of water. So the mouse is starting off at a higher elevation than the elephant. And the microphone's not picking it up, but Indy is meowing like crazy back here. So before starting the second problem, super quick break. Let me go play with your TA Indy a little bit, give him some exercise, and we'll come back and finish this last problem. All right, right, back to work. So for this problem, because of the height difference, the pressure at the two pistons are actually not the same as each other. On this drawing, P3 and P4 are equal, the pressure at the 2 points that are the same elevation. And P3 is actually going to be at a higher pressure than point 2. That is, from the mouse's piston, as you go deeper in the fluid, pressure increases. Pressure increases as you go deeper in depth. And you can solve for this change of pressure using the hydrostatic equation, also called the manometer equation, that the change in pressure as you go deeper in a fluid is going to be equal to rho gh. That is the density of the fluid times gravity times the change in height or the change in depth. So this time the equilibrium equation is that the pressure on the elephant side is going to be equal to the pressure under the mouse's piston plus rho gh due to that extra column of water, due to that extra depth. So we can plug in the same masses from before, put in the density of water and gravity and this 1 foot height, and we can see that the pressure due to the mouse on the piston generates 1.59 pounds per square foot. So not PSI, which is per square inch, pounds per square foot, but the weight of the water generates a pressure of 62.4 pounds per square foot. So actually the mouse itself will have almost no impact on the elephant side of this problem. The force being transmitted to the elephant is almost entirely due to this column of water. And solving for the new diameter on the elephant side, we get a diameter of 3.15 feet, which now is about the size of an elephant and does make this seem like a more realistic sort of scenario. So mechanical advantage at an equal elevation is very possible just by using the ratio of the two pistons. But if you want to use hydraulic forces to lift very heavy objects, don't only work at a constant elevation. Give your input force extra height. And that way your input force gets the additional help of that extra column of water that's also going to be applying force and pressure throughout the system. To learn more about pressure, watch this video next to learn about terminology gauge pressure versus absolute pressure, as well as how pressure gauges work, how we actually measure pressure.